So welcome to our session, and we'll start off with Oliver Bračevac talking about graph IRs for impure higher order languages.
Okay, is that better now? Yes. Okay, thank you. So in this talk, we consider graph-based intermediate representations for impure functional programming languages, specifically C of node IRs. And they've been used in imperative languages in JIT compilers, for example, like in Java and JavaScript. And they're actually pretty good for dissolving the rigidity in tree-based intermediate representations and give you a graph representation like the one on the right for this simple JavaScript program taken from V8. That's pretty good because we gain lots more flexibility in rearranging the code using code motion. And we have highly localized reasoning from the dependency structure, which unifies control flow graphs and data flow graphs. And that gives you access to very powerful optimizations using code motion and just looking at the graph dependencies. But let's say we add a function call here, then this all quickly runs out of steam. And it's usually in the scope of a single function and is not intraprocedural. And this is also decisively first order. So in this talk, we asked the question, how could we make those C of nodes IRs work for higher order effectful languages like Scala or Camel? So for example, what would be the graph for this kind of program, which is a rather imperative way to compute the size of a list using mutable state? And we have to avoid a couple of pitfalls or be mindful of them. So for example, we have higher order functions and first class functions, and they lead to imprecise control transfers, so we can't be sure what's being eventually called. We also have mutable states, and we have to deal with aliasing that also leads to indirections, and we have pervasively side effects. And the question here is now, how do we draw the dependencies? How do we get them at all? And that's also a matter of being precise and affordable. So we could do the naive thing and have a complete graph, but then it's totally rigid, and we can't move the code around. So we want to have more precision, but then we run into the territory of costly flow analysis like KCFA, and that gets quickly intractable. So we're kind of surrounded by uselessness, and we want to make this kind of work in a useful manner so that we get dependencies which are good enough for aggressive optimizations, yet relatively inexpensive. And can we also make this modular and support separate compilation and not have this whole program using these fixed point iterations, for example? And in this work, we make this all happen, and we bring C of nodes IRs to lambda and effect in a way that is supporting global optimizations, interprocedurally across function boundaries. It is modular, supports separate compilation. It's affordable, gives you precise effect dependencies, and it enables these aggressive optimizations for C of nodes for all these languages like Scala or Camel and friends. And this has been implemented in the Scala LMS compiler framework. We get super fast imperative functional code, and we have proven this stuff sound. So how do we actually go about this? How do we get the dependencies for higher order programs with effects? And the key here is that we abandon flow-based analysis like CFA and instead use dependent types and typing information. So we put all the relevant information into the types, specifically the context and capabilities of computations. And we rely on type inference, which is usually efficient in practice to compute dependencies and propagate results. There's two modes of use here that we propose. For general purpose languages, we rely, like in the usual type inference case, on lightweight user annotations that are also serving as documentation, and it is no more complex than Rust. And in more specific cases like DSLs, we can use the constructive nature of DSLs to hide the information for dependencies from the users and just leverage the constructive properties of the language. Naturally, we inherit the virtues of type systems and get modularity and separate compilation from that. And the foundation for this is reachability types, which I presented 2 years ago at OOPSLA, which is an ownership type system that supports higher order functional programs with effects seamlessly. So this crap down here is an arrogant schmuck, and he has every right to be, because he handles ownership and higher orderness and effects like a boss. And he reigns supreme in his natural habitat, the sea of nodes. Okay? So let's do a quick recap of reachability types to give you the idea how this works. In reachability types, we track sets of reachable variables and attach them to types. And that gives us a handle of what is aliased by values and computations. So for example, the C1 and C2 reference, they reach themselves. And once we have an alias like C3, which is aliasing C1, we have a reachability set at C3 that points to itself and the alias for C1. This gets more interesting if we have functions. So like this addref function that takes a reference x and adds it to C1, and then returns C1. If you look at the type, we notice that we have a reachability annotation on the function type itself. And that tells us what is actually relevant for the computation of addref and what can it actually see in the context. So what does it close over? And that also in turn tells us what is it oblivious of, what does it not observe. And that gives us a useful upper bound for the context for potentially effect dependencies. So that's kind of the gist of it. We support separation and overlap control in the user annotations for the parameters. So if we have this empty set here, that means we have total separation for call sites. So for example, we can call this with C2 because it's not overlapping with what addref can see, which is C1. But if we pass C1 or any alias for it, then this is a type error. So dealing with separation and overlap is kind of under the control of the user, and the user is expected to annotate those reachability annotations to parameters, and that's it. And we note we also have dependent types. So we have these effects, which are also reachability sets that tell you what operands are used, like an effects as capabilities model, basically. And this can depend on the reachability information of the concrete call site arguments. And we are using those to calculate the dependencies in the graph. We can refine this further to distinguish between reads and writes. So for example, addref writes C1 and reads C1, but only reads X, for example. And that's also pretty useful, as we will see later on. Let me give you now an idea how to calculate graphed edge dependencies from the effects. So this is a version of the program I showed you earlier. And the idea is we use the effect system to get the reachability set, which is relevant at each instruction here. And the idea is then that we look at the operands, and by reachability we know the aliases of the operands in the context. And for those we calculate the dependencies. So each operand in the set yields an edge. And what we are interested in is where was this thing last used in an effect? And that will be a control dependency, labeled with the name of the operand. And we can do this from bottom to top. I choose this here. And all what we want to know here is where was this last used? So the last use of a thing is where we point to the edge, okay? And then we also have data dependencies. They're not that much interesting. It's basically just free variables point to the binders. And then we can extract a graph representation, which looks pretty much like this. And you can see those purple boxes. And that leads to the next feature of our graph IR, which is lexical structure directly embedded in the graph representation. So if you want to support higher orderness, we better have a notion of a lambda directly encoded in the graph. So in this example, we have this simple function doing something with a reachable reference, and this would be its graph representation. And the important takeaway is we have a notion of binding inside this graph structure, and that has many benefits. For example, we can do seamless code motion and lambda hoisting pretty effortlessly in this representation, which you can't do in these older works on C of nodes, because they don't have a notion of binding. And since we have now lambda, we can also think in terms of lambda and have derived syntax, like control structures, also at the graph level, and it works pretty much in the same way. Another notable feature based on the refinement for read and write effects is we can have anti-dependence. So, for example, in this program, it's debatable whether we actually need those two statements, x2 and x3 in the middle, because we have this writes in the end that makes them unobservable. But how are we sure? We need to look at the dependencies. Do we have anything in the rest of the program that points to them? And we distinguish hard from soft dependency to make this possible. So hard dependency is something that can't be skipped during code generation, but a soft dependency gives you more leverage. and it is derived from the read and write effects in the sets. I defer to the paper. Okay. I defer to the paper for the specific details, but the intuition is if we have a node that is only soft-dependent by, we can safely skip it, and the dependent node can still be retained. So those effects, if there's no other dependency in the rest of the program, they can be just discarded during code generation. We have more interesting stuff about effects in the paper, specifically using flow-sensitive effects to model stuff like type state or uniqueness. And in one of the case studies, we use them, for instance, to have a safe embedding of mutable builder APIs for immutable data structures in pure functional programs. And based on these ideas I presented, lexical structure, hard and soft dependency, we have graph-level optimizations using these equational rules. They're pretty standard, like commutativity, various forms of common sub-expression elimination. The more interesting ones are at the bottom, like DCE, which uses the soft dependency notion to skip stuff, as I explained, and also lambda hoisting. And as I mentioned earlier, this is effortlessly doable. We can seamlessly move stuff in and out of nested scopes because we now have a notion of a scope inside of the graph structure. As a fine graph transformation, I want to quickly brush over function inlining. Since we now have lambdas in the graph level, it pretty closely corresponds to the notion of application and substitution in the term level. And all we want to do in a call side is, just paste the instance of the body here and patch up the dependencies. That's the more intricate part. And the high-level idea is that since we have a dependency type system and having type and term level substitution, this is also mirrored into a notion of substitution at the dependency edge level, and the formal details are in the paper. But leveraging this close correspondence to these term level intuitions and graph level intuitions, we can also have a formal meta theory for the graph IR that asserts that this is actually reasonable. And we went to the trouble of proving type independency safety, so we know that the synthesized dependencies are actually sound and correct and faithful of the program's control flow, and we also have developed logical relations for reachability types to show that the equation rules I showed earlier, including a function inlining and beta equality, are sound with respect to contextual equivalence using this logical relations argument. And this is all backed up by the mechanized meta theory from the previous work on reachability types, which you can check out at our local repository. And the full details for the graph IR based on these results is on pencil and paper in our 60-page companion paper on archive. And that was the result of a very intense reviewer discussion. Quite exhausting, I can tell you. And finally, we also have implemented this graph IR in the Scala LMS compiler framework. And LMS is a library in Scala for writing compilers. It supports multi-stage programming. And we re-implemented several older papers that use LMS to speed up domain-specific languages on top of the new graph IR and compared to the old versions. And all throughout, we squeeze out a little bit more performance using this effect of our graph IR. And also as a teaser for yet another conditionally accepted POPL paper, there's a data log compiler that also uses this work. I'm not involved in this, but it's derived from this work. And we also get very decent speedups for data log in all sorts of workloads. Okay, so to summarize, hurrah, hurrah, higher order graph IR. And, this is all made possible by using all sorts of cool cutting-edge PL techniques, ownership types, dependent types, and type inference. I might add those are not the scary dependent types that you use for explaining COC or AGDA, but they are baby dependent types. It's just path dependent types, a bit of substitution at the type level, and that's how we propagate the information, instead of using these flow-based analysis like CFA. And we have a strong formal meta theory. This is all correct. We know what we're doing. In the paper, there's more cool stuff. For example, we detail the algorithm for code generation, how to go back from graphs to trees. And there we can also do some variations. For example, we have a cool and very inexpensive frequency estimation that kind of moves expensive codes from hot paths into more colder paths, for example. And also we discuss higher order programming optimization, like lambda lifting, super beta inlining, just with the graph, we can support restricted cases, but for the full deal, you need to complement our approach with the usual context-based flow analysis. Finally, check out our artifacts. The Scala LMS version with effect dependencies, which has been brewing on GitHub for a while. Also the reachability types repository. And if you find the LMS code base too daunting, you might also want to check out our mini prototype for this approach that runs in the browser. Thank you very much.
Hello, this is Amir from the University of Edinburgh. So I have one small question. So is it in Scala 2 or Scala 3?
Scala 2.
Yeah, and for now, a follow-up question. For the type inference and all this kind of stuff, do you rely on the host language, or it's basically somehow you use these notions and you implement the type inference by yourself?
Could you repeat the first part of the question? I didn't understand it.
Yeah, so for the kind of the type encoding that you have, and you're saying that basically everything is just type inference. So are you relying on the Scala compiler to do the type inference for you, or you're implementing the type inference by yourself?
Well, we implemented the type inference within the Graph IR implementation of Scala LMS. It's not like we're using the Scala compiler to infer the types, because it doesn't have a notion for tracking the set of variables. But on a related note, we could probably use this experimental capture types proposal for Scala 3 to have to leverage this for tracking the sets of variables and inferring them.
Okay, thank you.
Okay, can you take one more question? Next speaker.
I think you should pick a question.
Oh, right, sure.
Great talk. So, C of Node seems to have fallen out of favor in the industrial context I heard about. And my understanding is it's hard to work with. Have you found something like that, or do you think it's really the right representation?
Well, naturally having used this in Scala LMS, being the author of this work, I would say it's, for me, easy to use. But I think, especially in this context, it's actually really easy to use, even not just my opinion, because LMS is, all the case studies that we implement this with are DSLs. And as I explained in the beginning, we can hide lots of the complexities of the type system from end users. But I guess if the question is this easier for the language implementer? I think you need to have, well, you have to have a good idea of how reachability works.
Okay. Thank you, Oliver.
Thank you.